United we stand, divided we fall. This statement about the importance of unity was first told by the ancient Greek storyteller Aesop more than 2000 years ago, and is still very valid up until today in our digital life, especially in the high-stake critical service like cryptocurrencies. In fact, many previous work emphasize that only when united, or to be precise, well connected, cryptocurrencies can deliver reliably the promised services. In this work, though, we saw that united cryptocurrencies may still fall. And to disrupt cryptocurrencies, we uncovered a new attack target known as mining pools. At the high levels, mining pool consists of several miners, where each miners run dedicated hardware, such as a ZIG mining device. And typically, miners in a mining pool are coordinated by one or more central servers to create new blocks to extend the blockchains. In practice, multiple mining pools exist and they compete to create new blocks for the rewards in form of new cryptocurrencies in return. 15 years ago, we didn't need to participate in a mining pool to create new block, but this is not the case anymore nowadays. In this plot, we saw the portions of new block in the top 10 proof-of-work cryptocurrencies that are created by a mining pool. And we can see that mining pool actually account for most of the new cryptocurrency block being created nowadays. For example, more than 99% of new Bitcoin blocks are created by a mining pool. So essentially, mining pools are crucial for cryptocurrencies. And in this work, we introduce the erosion attacks that disrupt mining pools using routing capabilities. Let's first discuss how the adversary can do that. In our threat models, we consider the adversary control a malicious autonomous systems or AS. Indeed, our public internet consists of almost 80,000 autonomous systems that handles the traffic from one point to another, and some of them can be malicious, such as the autonomous systems controlled by nation-state adversary or the ones that have been compromised by cyber criminals. In the erosion attack, the adversary first identifies the vulnerable mining pools. And in our context, the vulnerable mining pools are the ones that have accessible pool servers that the adversary can identify the IP addresses. We did a comprehensive survey of 55 active mining pools in the top 10 cryptocurrencies, and we found out that 50 or 91% of them can be targeted for the attacks. Once the adversary knows the address of the pool server, the adversary can intercept the connection between the pool and the miners, either naturally because the adversary is already on the path of the connection between the pool and the miners, or the adversary can use routing manipulation techniques known as BGP hijacking to hijack the connections. To do so, the adversary needs to send bogus BGP messages, and in this example that I have, the pool server is hosted on AS10 and the adversary AS66 is trying to hijack its connections. To do so, the adversary can advertise BGP messages that claim the AS66 is the origin or the owners of the /24 prefix hosting the pool servers. And this technique is known as origin hijack, which already exists for decades. And to handle origin hijacking attacks, AS often rely on a cryptographic framework called RPKI, which stands for Resource Public Key Infrastructures. And under RPKI, AS10 can associate itself and the prefix that is authorized to advertise. And thanks to that, any unauthorized advertisement from the adversary will be filtered and discussed by any routers on the internet that enables API validations. But unfortunately, the adversary can still perform a so-called false origin hijacking attack to bypass API. Particularly, the adversary can announce a message with AS10 as the origin and AS66 in front of that. And as a result, traffic going toward the pool server will still be intercepted by the adversary even when AS10 enable API. We did a survey on how well mining pool in the top 10 cryptocurrencies protect themselves from the hijacking attacks. And we found out that 93% of the pool server are actually protected by API. And this suggests that mining pools are well aware of BGP hijacking attack and actively defend against the hijacks. Of course, as we already saw, these pool servers are still vulnerable to the false origins hijacking attacks. And then the robustness of the pool servers against hijacking attacks boil down to whether the pool servers are hosted on the max length prefix. This is because the internet forwarding prioritizes sending traffic to the more specific, longer prefix. And as we can see from this plot, only 52% of the pool server are protected by the max length prefix. And this means that the rest of the pool server are actually vulnerable to sub-prefix hijacking attack, where the attackers advertise a longer or more specific prefix to hijack the traffic. And once the adversary intercepts the connection between the pool and the miners, the adversary can simply drop them off. And by doing so, the adversary effectively destroys the powers of the victim mining pool. Alright, so we have talked about how to disrupt mining pool with routing capabilities. Let's discuss how to make the attack stealthier. And of course, it is the elephant in the room that hijacking and dropping the traffic of the mining pool can be quite visible. And there are two main reasons for that. First, the adversary may need to perform a long-term BGP hijacking attack as long as the follow-up attacks against the blockchain need to be. For example, an impactful double spending attack followed by a BGP hijacking attack may need several minutes and even up to hours to be done. And such a long-term BGP hijacking attack often cause a lot of attention from the network operators or even security investigators. And second, if the adversary drops the packet in the intercepted connection between the pool and the miners, the affected victim will immediately detect it. And this is because the internet nowadays is actually quite resilient to packet drop and often achieving less than 1% of packets lost. And does that mean we don't have to be worried about the erosion attacks anymore? Unfortunately, the answer is no. We actually discovered vulnerabilities in the mining pool protocol that enable stealthier attacks. We will come to the details of the vulnerabilities in 1 minute, but at the high levels, the adversary only need to perform a few packet tamperings instead of dropping all the packet that the adversary intercept. And thanks to that, the adversary only need to perform short-lived BGP hijacking attacks, which are often ignored by the network operators because such short-lived BGP hijacking occur quite frequently on a daily basis due to, for example, misconfigurations. Alright, let's talk about the vulnerabilities that we discovered. But first, we need to understand what is a mining pool protocol and how it works. In the last decade, Stratum, or Stratum version 1, has been the dominant protocol despite that it provides no encryption in the communication between the pool and the miners. Basically, the pool aims to create a new block with certain number of leading zeros in its hash. The pool sends the job to the miners, where each job contains a block template of transactions and assigns the miners to find a block with a fewer leading zeros in its hash, which is basically easier for the miners to create than the actual target block. Once the miners with a dedicated device find such block, they send the results back to the pool, and these results are known as shares. Since each share has some probabilities of becoming the actual block, this process is repeated until an actual block is found. And afterward, the miners will collect the rewards accordingly to the number of shares that they submitted. Recently, the blockchain communities has developed the next generation of the Stratum protocol called Stratum version 2 or V2. Amongst many new features, Stratum v2 support authenticated encryption with associated data in the communication between the pool and the miners. In particular, the message senders and the receiver independently maintain a nonce counters used for encryption and decryption. Once a message is successfully delivered, both sides increase their counters by 1, such as from 19 to 20 in this example. And we know that each side will maintain the sender's counters and the receiver counters separately. So when the miners send back the message to the pool server, the counter that we saw here remains the same. So what is interesting in the encryption of Stratum v2 is that it has vulnerabilities in handling decryption errors. For example, if a packet is corrupted on the wire, the receiver cannot decrypt it, and therefore the receiver counters remain the same at 20 in this example. And meanwhile, the sender counters is already increased to 21 because the message is successfully sent from the sender side. As a result, the miner keeps working on the outdated job and ends up with a rejected share. And what is worse is that the counters are now out of synchronization, so that the receiver cannot decrypt any subsequent message. These vulnerabilities allow the adversary to tamper with a single packet in each of the intercepted connections and persistently disrupt the connections so that there is no mining progress at the miners at all. Of course, after an extended attack period, the pools and the miners may observe the effects of the attack. For example, the miners may notice insufficient reward according to their submitted share, or the mining pool may notice a decrease in its total mining power. However, due to a lack of trust between the pool and the miners, pool and miners often point the finger to each other in these scenarios. For example, miners commonly assume that the pool are cheating and have stolen their reward, while the pool may assume that the miners are facing some hardware failures or the miners have been switched to allow the mining pool. And thanks to that, the actual perpetrators of this attack likely stay under the radars. And more importantly, even when the victim suspect of something wrong is going on with their connections, it is fundamentally difficult to trace back the root cause of a few packets being tampered, because even in the internet nowadays, it may happen even without any attacks. And not just attacking a single mining pool, we saw that the adversary can perform large-scale attacks by attacking multiple mining pools at once. Here we saw the ratios of the mining power in Bitcoin that can be disrupted on the x-axis, and on the y-axis is a numbers of potentially malicious AS that can perform such attack. And there are three important data points that I would like to highlight. First, almost all AS on the internet can disrupt up to 45% of the Bitcoin mining power right now. And second, there are more than 1,300 of different ASs that can destroy half of the Bitcoin mining power if they want to perform a follow-up attack against the consensus of Bitcoin. Exceptionally, we also found that Cloudflare is the most powerful AS that is capable of destroying up to 96% of the entire Bitcoin mining power. So far, we have talked about how to disrupt the mining pool with the routing capabilities while being stealthy. Now, let's talk about how to mitigate these erosion attacks. The easiest mitigation to the attacks is patching the vulnerabilities and particularly fixing the protocol so that once the client cannot decrypt the message, they should reset the connection with the senders. And as part of our vulnerability disclosures to the developers of the Tran protocol, the patch has been implemented and merged into the main code base of Stratum protocol since February this year. And once the vulnerability is patched, the adversary still can go all the way and disrupt all the connection that the adversary intercept. And to deal with that, we also propose several short-term countermeasures for the mining pool, which aim to have more decentralization and more secure routing for their pool server. And by decentralization, we mean that the pool should host their server on multiple ASs. And by secure routing, we mean that the mining pool should host their servers on RPKI enables and MAC9 prefix. And indeed, with those short-term countermeasures in place, the number of potential malicious AS that can perform large-scale attack decrease significantly. For example, no adversary AS could destroy more than half of the Bitcoin mining power. Of course, we envision mining pool to have even more decentralization and secure routing. For example, mining pool could shift to decentralized protocols like the 5 mining pool that are not vulnerable to our attack in our surveys. And of course, more research needs to be done so that we can have a good trade-off between decentralization and performance, which have been missing in the previous protocol. And another long-term countermeasures could be to realize routing awareness in the connection between the pool and the miners so that they can avoid certain suspicious AS on the path. To summarize this work, we find that mining pools are crucial to cryptocurrencies, but they are extremely vulnerable to routing attack. We also discover vulnerabilities in the soon-to-be default mining protocol called Stratum Virtue that enables stealthier attack. For future work, we suggest critical service like mining pool should embrace more decentralized architectures. And with that, I would like to thank you all for listening, and don't hesitate to contact me if you have any questions.